Okay, welcome everybody. In this lecture, we are going to discuss about audio signals. So we see speech around us. So many people, they speak so many languages. In this room itself, I expect we should have at least 3-4 languages being spoken, right? I speak Punjabi, Hindi, English. What other languages do you speak? Telugu, Konkani, any other language? Bhojpuri? Why didn't you say that? Bangla? Okay, I'll know a little bit Bangla. Okay, Marathi? Nobody? Okay, so we have so many languages. Then we have music.
Sari ga re ga pa ga re sa.
So here in the audio, what did you saw? What did you see? What all the instruments are playing? Somebody is singing vocal. There's a tanpura, constant kind of drone sound, and then tabla. So all these instruments are playing in this audio. So this is all we see around us. How do we process them on a computer? When I speak something, this goes to a microphone. What does a microphone have? Microphone has a vibrating membrane. Right? This membrane is vibrating as the sound falls on it. And these vibrations now need to be captured. How do you capture the vibrations? How do you convert motion into electric signal? By some transducer, right? So the principle is that when something moves in the magnetic coil, then you get electric signal out, or you can have also piezoelectric effect where when a crystal is pressed, you get some electric signal out, right? So the basic principle is to convert the motion into electric signal. And then that electric signal goes to your computer and it is saved as a waveform. But something happens here, which is called sampling and quantization. So sampling means you have an analog signal, analog electric signal, and you have to sample it in time and then quantize it in levels. We saw this in the last lecture that sampling, you have to take care of something called Nyquist sampling theorem, which means your max frequency should be less than half of sampling rate. Means sampling rate should be more than twice the max frequency. And then now question is, what frequencies can human hear? Our ears cannot hear all frequencies. If let's say I play some audio with a frequency less than 20 hertz, we can't hear that. And similarly, if I play some audio with a frequency more than 20 kilohertz, we can't perceive that. How many of you hear bats in the night? How many of you hear bats in the night? How many of you see bats in the night? But nobody hears bats because they speak or they cry at a frequency much higher than 20 kilohertz. So we can't even hear that. Our ears can't vibrate that fast or can't perceive that sound. So then when we are saving audio into our computer, what is a good sampling rate? So it's 40 kilohertz. So that's what we get in CD recordings, uh, high quality recordings. I mean, decent quality means they are very good quality high CDs. So there we get 44.1 kilohertz, which is slightly more than 40 kilohertz. Then what about quantization? Quantization means we want to convert a number, continuous number, into a discrete number, rounding off in simple words, right? So how many levels do we choose? If we choose uh, q levels, no, not q levels, but q bits, because we have made some levels, let's say n number of levels. Now we have to represent those levels into binary form because our computer can save binary form. So let's say we choose q bits to represent that number. So how many possible levels can be formed using q bits? 2 to the power q, right? Let's say if we have 4 bits, like every number I want to save in just using 4 binary numbers, this means 2 to the power 4, 16. 16 levels are possible. So I make those 16 levels. And so generally in the CD quality, means the good quality, it's good in the sense that it is high quality plus it is also cost optimal. You can't make it very large, very high quality because humans can't perceive it, then you are losing on money. So CD quality, when I say, it means some optimal number that quality is also good and the size is also very compact. So 16 bits per sample. So which means 2 to the power 16 levels. So this is anyways quantization, which you have seen. Okay, now let's come back to waveforms. So when you convert your audio into this quantized signal, it's called a waveform, right? You have seen dot wave files. Wave files, right? You save your audio into, when you record your audio on your computer or on your mobile phone, it will save it as most probably a dot wave format, right? So it is basically that quantized and sampled signal. Now there are tools like Audacity. Audacity is a tool you can install on your computer. It's free of cost. You can open source tool. And there you can see the audio file, what is there in it. For example, in this audio file, I have 3 channels. The first channel contains exclusively tabla. Second channel contains exclusively drone. Third channel contains exclusively the human voice. And you can add all these channels or mix all these channels to get a fourth channel, which is the mixture, which you just now heard, right? So is this clear now that how audio file is stored or what it is actually inside that wave file? Uh, so as I told you that you have a vibrating membrane, it gets converted into an electric signal. This is a continuous time signal. So you sample this signal to get a discrete digital or discrete time waveform. And then you quantize it as well. So that is the waveform which we get. No. So, okay. So it's like this. So you have, this is my time dimension. When your membrane is vibrating and then, okay, let's say you got the electric signal. Electric signal is something like this, right? Right? Now you sample it in time. I will use some other color pen, maybe a green pen. You take a sample, 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 like that. So you're sampling that um, voltage levels which are changing with time. So you're sampling it in time and measuring its value. Oh, it's now 1 volt, 1.1 volt, 1.11 volt, like that. And the time grid is regular, means uniformly spaced time grid. If you make it non-uniformly spaced, then you may not be able to use FFT kind of algorithms, but there are other mathematical ways to compute the Fourier transforms, but it will be computationally much more expensive. So we use a regular time grid, which is very easy to implement in real life. Okay, any more questions? No question. Okay. Now we got the waveform. Next thing is that we want to process it, right? We want to do speech recognition or we want to do music recognition. We want to do identify who is speaking. We want to find where is this particular word in this audio file. So many tasks. We want to denoise it. We want to extract only the vocals by subtracting all other sources of audio. All those things are possible using this waveform, this wave file. Okay. Now I'm going to discuss how do we mathematically model any audio, right? So first thing is, if you look at the waveform, it is dynamically changing in time. But what remains constant or stationary is the local behavior. If you take a very small window, let's say a very small window in this waveform, and you plot it like this, what you see here is a kind of stationary pattern. And this pattern is huh, periodic. What do you do for periodic patterns? Very useful tool. Fourier transforms. What did you say? Power series. What's that? Like Taylor, Taylor series expansion. Power n, power j. Okay. Yeah. Mm, yeah. Maybe that could also be one kind of transform, but this Fourier transform is a common one which everybody uses. So let's see what's a Fourier transform. Okay, by the way, the tool which I used in the last slide is called Prat. This is also an open source free download tool. You can download it on your computers and you can do many interesting things using this tool, Prat. It is a little bit more powerful than Audacity to do detailed analysis. It has many more functionalities available. Uh, Audacity is good for simple tasks, but on very large number of audio files, and it has many more production kind of implementation. But Prat is more like research oriented, where you can really do many things on single audio file, right? So both these tools are very nice, and I would highly recommend you to explore these two tools. Then coming to Fourier transforms. So what is the Fourier transform we saw in the last lecture? It's simply x multiplied by some complex sinusoid, and you get different xk. So we saw this example also in the last class, that if your audio signal is, or your signal is periodic with a sine 2 pi some frequency into n, then you will get a peak in the spectrum. And where will you get the peak? We saw in the last class, we did derivation also. What will be the value of k for which the peak appears? The peak will appear at that particular value of k. And you will get a mirror image here. Uh, and the good thing we saw is that if you have multiple sinusoids mixed together, this Fourier transform can also decouple it or decompose it into different peaks. That was a very useful property of DFT. Uh, if you want to read more about Fourier transforms, then there is a book called Oppenheim. I am sure if you have done E200 course, you must have seen this book. Uh, uh, so here you see that intensity is changing. In one example, I'm speaking softly. Other example is a bit louder. Now the question is, how do you quantify intensity? Now you know about waveforms. Can you tell what is the intensity? Like if I give you two waveforms, can you tell me which one is louder than the other? Yeah, that's good. So this is the uh, waveform. This is how the waveform looks like, the top one. This is the waveform. So you can see here the amplitude is quite low here, amplitude is quite high here. But then which sample should you pick? Which sample should you pick to look at the amplitude? Which sample? Um, let's say I'm not interested in single frequencies. I want to look at the entire um, loudness, intensity, loudness which I hear. So how will you quantify that? So average all the amplitudes, no? Just take an average. So that's what is you do. You take the amplitude at every sample in a small window, let's say, and then average it. That gives you the power in that window. And from there, you can quantify which one is louder, which window is louder, right? If you take a window in this audio, you will get lower intensity, lower power. Here, you will get more power or energy. Okay. So now look at the spectra. How the spectra look like. If I take a small window in this waveform, spectrum looks like this. And if I take a small window in this waveform, spectrum looks like this. Can you tell from spectrum which one is louder? Notice these numbers, 48 and 53. Huh? Yeah, so this one is much louder. Now the question is, how do we quantify the amount of loudness? Again, look at the energy in that spectrum. How do you measure the energy in the spectrum? Okay, that is there on the next slide. Huh? Yeah, something like that. Let's look at the next slide for exact mathematical formulation. Quantifying intensity. So one thing is that you take the sum over all the squares of amplitude, that becomes the energy of your signal, right, from 0 to n minus 1. The energy is given by mod xn square, sum over all n. Now, if you look at the DFT or the spectrum, then there is a nice equivalence. What's the name of this equivalence? Louder? Increase the intensity. Parseval's theorem, right? Can you derive it? So that's your exercise. Derive it. You know the basic definition of xk. From there, you can directly derive this. That's a homework for you. Now the thing is, intensity can be written as either this or this, right? You sum over all the squared samples, amplitude, square amplitude of all the samples, or you sum over all the squared amplitude of squared spectral power, squared spectral amplitude, and then you average it. There is a factor of 1 upon n extra here. That's just a mathematical construct. When you derive, then you will get this factor extra. That's intensity. Is this clear? Good. Now a twist in the story. Our ears are more sensitive to lower intensities than to the higher intensities. I'll give you an example. For example, our ears can very easily differentiate I1 and another intensity I2 plus I2, which is I1 plus constant. This C is constant. Huh? So let's say if I take one sound at intensity I1, another sound at intensity slightly higher than I1, that the difference of intensity is same. Now, when this I1 is smaller value, I am much more sensitive. I can make out this I1 and I2 difference very easily. But this I1 is a larger value, then for me to differentiate these two sounds or these two intensities becomes difficult. Like when I say uh, means not the frequency, but look at the intensity part. It's easy to determine. But if I shout very loudly, ah, and then again shout with the same difference C1, you can't make out the difference in the two intensities. So now the question is, how do we become efficient in representing these? So the answer is, we use a log scale. What does a log scale do? The log scale also, if you make slight change when the value is small, I1 is small and I2 is C1, some value C more than I1, then log of I1 and log of I2 are very different. But if you go to very large value, I1 is very large, then log of I1 and log of I2 are quite close. Does that make sense? So that helps us in efficiently representing our uh, values. So this is called the decibel scale. So what is decibel scale basically? You take your intensity, take log, multiply with 10. Multiplication with 10 is just a conventional thing. And this is called the decibel scale. So when I say I'm speaking at a 10 decibel uh, intensity versus 11 decibel intensity, this means you can derive the intensity from here. Right? Okay. Um, Now, if you look at the spectrum on the decibel scale, it looks like this. You can see here, let me help you appreciate this point. There is one peak here, there is one peak here, maybe a slight peak here, another peak here, another peak here, like in the envelope, right? And you can see the envelope very clearly, that thing how things are changing. This is because this is on the decibel scale. If it were on the linear scale, how it would have looked like? It would have been something like, yes, you have a high peak here, and then everything is almost zero, and almost flat, because uh, of this reason, that the values, this large value and then small values, even if our ear is very sensitive to these values, but a linear scale does not capture it very well. Is this point clear? It is slightly, you have to think a little bit that why we are doing this, but it's a very clever thing to do if you want to be efficient in your representation. Okay. Now we move to the next topic, which is pitch. Listen to this carefully. What's changing now? Pitch. It's like I'm singing different notes as if. Now look at the waveform and the spectrum and tell me what is changing. Frequency, right? The fundamental frequency. So, uh, and in the spectrum, what was changing? In the spectrum, what was changing? Amplitude of what? The peaks are shifting, right? Because if your frequency changes, then your value of k will change in the xk. The peak will appear at a different k, a higher k, if my frequency increases, right? So my fundamental frequency peak is shifting. Okay. If you want to examine pitch, the question is, what should be your window size now? What should be your window size? Your window size should be such that it captures at least a few cycles of your frequency, right? Let's say if I have a signal which is like this, and you choose a window which is like this, will it capture frequency? Will the DFT capture frequency? No. You have to choose at least a few cycles, maybe 3, 4 cycles, to be able to get the peaks at the right K values. Is that clear? So this is very important point. So generally when we speak, when I sing, let's say my frequency will be around 200 hertz, fundamental frequency. There's harmonics also, but fundamental frequency is around 200 hertz. So what should be the size of my window? So my F naught is about 200 hertz. What is T naught? T naught is 1 upon F naught. So how much is it? 1 upon 200 is how much? 0.5, no, sorry, 0.005 seconds. So it's 5 milliseconds. And if my F naught is, let's say, 1000 hertz, so if I sing at a very high pitch, we ladies sing at a very high pitch, so they can reach 1000 hertz. Or if I play some instrument, okay, but let's stick to only what we can sing. So the frequency here, the T naught is how much? 1/1000 is 1 millisecond. And if I sing at a really low pitch, uh, so it will be, let's say, how many? 70 hertz or something. I don't know. What is a T naught? 1/70 is how much? So let's say 1000 upon 70 milliseconds. So which is how much? 14. Okay, let's say around 15 milliseconds. Okay. So now tell me what should be the size of my window so that it effectively captures the F naught information. Huh? Yeah, around 50 milliseconds. Huh? So my window size should be around more than 50 milliseconds is better. So that's roughly the thing which we use. So if you use very small window, let's say 10 milliseconds window or 20 milliseconds window, it may not capture that information. Okay. Now, once you got a window, you can determine the fundamental frequency using cross correlation of Xn. We saw it in the last class. You have a periodic signal. You want to find the fundamental frequency. If you take the cross correlation, you get peaks at the time period, right? Or if you look at the spectrum, then the first peak will tell you the fundamental frequency, or you will also see a pattern that harmonics are repeating. Right? Let's say you got at F naught, 2 F naught, 3 F naught, 4 F naught. So that structure you will see. From there, you can tell what is my F naught. Easy. These algorithms are implemented in Pratt, maybe in Librosa also. Sorry, maybe in Audacity also. I'm not sure about Audacity, but in Pratt, definitely it is there. Now, question is, how do we quantify pitch? Listen to it carefully. When I said this sound, what is the pitch now? What is the fundamental frequency? 122 hertz. This is the first peak, and also you can see that things are repeating at 122 hertz. It's called a COM structure, right? COM, you look like a COM, no? With F naught, 2 F naught, 3 F naught. That COM is there with a spacing of 122 hertz. Now listen to the next sound. Right? So it's higher frequency. How do you find out? From the spectrum. What is the frequency now? 143 hertz. Right? Now listen to this one. Still higher. What's the frequency now? 163 point something. 160.7 hertz. All right. So now you know how to find the pitch or the fundamental frequency of an audio by looking at its spectrum or by looking at its waveform. You can do it, right? Now, twist in the story. Our ears are more sensitive to lower pitch than to the higher. What does that mean? It means if I have some sound at a fundamental frequency P1, another one at P2, which is some constant C more than P1, then I can, if P1 is a very small value, let's say 100 hertz or something, I can differentiate very easily P1 and P2. But if it is very large, well, let's say 2000 hertz, then it's very difficult to differentiate. For example, 100 hertz versus 110 hertz. Anybody can tell these are different frequencies. But 1000 hertz and 1010 hertz, very difficult to distinguish. Maybe those who are very trained, they can distinguish, but ordinarily people won't be able to distinguish. There are beats. Is that beats? Uh-huh. Yeah. Yeah. Means, yeah, in music we use different effects to enhance these pitch differences. But I'm saying an ordinary human ear, means we become less and less sensitive to the differences as the pitch increases, given the difference in pitches remain constant, right? So, for example, in music, when you say sa, it has a frequency, let's say 100 hertz. Let's say my sa is 100 hertz, let's say. Now, what is the frequency of re? I'm sorry, I didn't intend to do music here, but let's do it because you asked. So let's say my frequency of sa is 100 hertz. What is the frequency of re then? Yeah, something of that sort. So 2 to the power 1.12, 2 by 12. So if it is the Shuddha ray, so 1 upon 6 or 2 by 12 into 100 hertz. But let's say if my frequency of sa is 1000 hertz, what is my frequency of ray? To the power 6 or 1.6 into 1000 hertz. Can somebody compute quickly what is this to the power 1.6? It's difficult, no? Let's say it is something 1.1. Let's just for example, it's 1.1, then it becomes 110 hertz. 1.12. Okay, so let's approximate as 1.1. This becomes 1100 hertz, right? So look at a lower frequency, you need only 10 hertz to change your note. And here you need 100 hertz to change your note. That's what I mean to say, right? Even musically, this effect is captured. Our ears are, when I say sa versus re, our ears are sensitive. And at higher frequency, also sa versus re, our ears are similarly sensitive. But the amount of C you need to make that effect visible at the higher frequency is very large. So hence, we use a log scale again, and not decibel. I'm sorry, this is not decibel units. This is we use uh, some other units. We use a log scale, but what are these units? These are the mel units. Let's say mel is one unit. Some people use bark, some will use cents, which are just some modification of the same thing. But let's look at this formula. This formula is some constant into log 1 plus f upon 700 mels. Right? You are basically doing a log transformation. You may ask the question, why are we adding 1 here? What could be the logic? It won't become negative. This quantity is never negative. Even if your f becomes 0, this quantity will become 0 because f is positive always. So this quantity also will be always positive, but it follows that logarithmic scale, right? And these constants are just determined to fit some data. Means people that did some psychoacoustic experiments, they made somebody sit and listen to different sounds and tell how much sensitive they are, and they did it with multiple subjects, came up with some curve. To fit that curve, they use these coefficients or these numbers. So nothing to worry about. The main principle is it's log of f. Because in decibels, conventionally we allow it to go to negative values. Right? If somebody tells you it is minus 10 decibels, you won't mind. But nobody will tell you minus 10 mels. Just convention. Okay. And if you look at the plot, if you plot it, it will look like this. Is it visible at the back? No, come in the front then. You can come. I'm sorry, next time I'll be more careful to make bigger pictures. So this is frequency, which is the F thing. And this on the y-axis you have the m thing. On the x-axis you have f, and on the y-axis you have m. So you can see how it looks like, right? As your f increases, your curve bends like this, logarithmic curve. Others can also come in the front. Feel free to move forward. You will see better. Okay. Is that well taken? The pitch thing is understood properly, right? So if I give you any audio file, you can tell me what is the pitch just by looking at its waveform or the spectrum, right? Now let's come to the next. So you see the audio file is very rich, right? It has so many information. Say intensity is there, pitch is there, and now we discuss about phonemes. At the same frequency, at the same fundamental frequency, and at the same amplitude or intensity, I can tell you E, U, same intensity, same fundamental frequency. What is changing? What's changing here? Waveform is changing in what way? So let's see that. So let's look at the waveforms. The waveforms will look different for a, e, ma. These three sounds are a, e, right? Let's look at their spectra, because spectra you can easily read. When I say a, you can see here there is some peak here, some peak here, like that, right? When you say E, you see one peak here and then slight peak here and one peak here. When you say you see this peak here, maybe then some small something here. So what is changing? If you notice the first peak here or the com spacing is same everywhere. The com spacing is not changing because fundamental frequency is same for all these three sounds. The average energy won't change. The average energy in this spectrum won't change much because it's same intensity, similar intensity. But what changes is the distribution of intensity. Yes. At what scale? If you look at the scale of one peak, it's yeah, it's different. But then when I say uh 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 so here also distribution is changing um, because peaks are shifting. But if you look at a small window around that region, let's say you divide this region into a small window. Let's say take this envelope. This envelope, you see, the shape of the envelope won't change. To keep it simple, the shape of the envelope won't change. When I say and the peaks have shifted like that. Okay, I will tell you with an example. Let's say I have this. So when I say I could have peaks here. And when I say at a higher frequency, let's say take green, I may have peaks here. Much more intense, much more dense, sorry. Right? But what is not changing is the overall envelope. That is not changing. So that's how we try to capture the phoneme information, right? So you got it right. Number one, intensity is there in the average energy. Pitch you can know from the fundamental frequency you can know from the com spacing, and the phoneme you can know from the envelope of this comb, the spectral envelope. Now look at other sounds. Let's say these are non-periodic, aperiodic sounds, but still you can plot the spectra, and this is what it looks like. Can you see what is the fundamental frequency of What's the F naught for sound? S sound? It has no F naught. It has no comb structure, right? So it has no comb structure. Sound, sound does not have any comb structure. But you can still get energies in small windows or small frequency bands. In sound, you see a very large energy in high frequency regions. Very large energy in the high frequency regions. Okay. Why Alexa is called Alexa? Why did they choose Alexa? This word, keyword, the wake word. When you say, Alexa, what's the time? They could have called it anything else also, maybe Amazon or Apple or something. But why Alexa? What is so special about Alexa? It has sound. And it is very easy to identify this sound because other sounds generally have high energy in the lower frequency bands, but this sound has a very high energy in the high frequency bands. So it's very easy to detect this sound. And when you say Alexa, it has to detect when somebody has said Alexa. So that's why they chose the word Alexa. Somebody told me this because I was working at Alexa, so they said this is why we call it Alexa. Okay. So and if you call it something with sound, it will be very difficult to identify to detect that sound. Let's say if I say uh, fan, it's very difficult because fur has such a low energy almost everywhere, and so but sa has very high. So that's one anecdote about sa sound. Okay, is that clear? At least the intuition is clear. Now let's quantify it. So how do we quantify the phoneme information? Uh, so look at the spectrum. So here my x-axis in uh, hertz and y-axis is in decibels in this spectrum. Okay. Consider a small window, or since it's a frequency, you can call it a small band, frequency band. If you look at the energy in this frequency band, right, it will try to capture the spectral envelope. Right? Let's say if I take one small band here and small band here and small band here and small band here and small band here, these, and if I take all these bands now together, means energy in this band, comma energy in this band, comma energy in this band, and a vector, it approximately tells me the envelope of the spectrum, independent of the peak positions. Right? Peaks can move slightly here and there, but the band energies won't change much, or their relative values won't change much. Even when intensity changes, their relative values won't change much. So take this small window. Let us call this as the WBK, the in the band, in the Bth band. Your window in the Bth band means this K means this is K. This is basically K here. Right? So your this window, let's say it could be a Gaussian window or a square window, whatever window you like to take. And then you compute the average energy in this window, right? That let's call it as YB. For the first window, YB is let's say 50, second window it is 40, third window like that, some values. Now take log of YB. Now see, when I computed this expression, I did not use decibel scale, huh? I just use the regular spectrum value. So just to make it something resembling decibel, take a log of this. Now, how do you take these windows? Like take these windows, overlapping windows, and cover the entire length of your frequency axis. Something like convolution, right? You take the window, move it by some hop size, then move it by some hop size, that becomes like, so you get basically values of yb for multiple values of b. B is equal to 1, so on up to capital B. Right? So this is first B, second band, third band, and the bth band. Then what you do is, for example, if I take 40 such bands, I get a 40 length vector. This vector tells me the what phoneme it is. Right? So you can represent pitch as a scalar value, intensity as a scalar value, but phoneme is not a scalar value. You have to use a vector to represent phonemic information. Is that clear? Simple. Um, so what we derived just now is, how do you, given a audio file or a spectrum, for every spectrum you can get 40 log filter bank energy values. Why is it called filter bank? This one window is one filter, right? What is a filter basically? Uh, okay. Conventionally, filter means convolution in time domain, which is multiplication in frequency domain. This frequency domain, you're multiplying a window, so it's like a filter in the time domain, right? It's called a filter. It's appropriate to call it a filter. So why it is called filter bank? Because you're using 40 filters. So it becomes a bank of filters. And log because we took log, energy because YB is the energy originally. So log filter bank energies, LFB representation or features. Okay, now one small point I want to mention here is that these uh, filters are in the Mel scale. Why? Because we know our ears are more sensitive to lower frequency regions and less sensitive to in the higher frequency regions. So when we are convolving, we are using a filters which are linear in the Mel scale, right? But if you map it to the linear scale, it will be exponentially increasing in width, right? Let's say my width in the Mel scale, here it is C width, here it is C width. When you come to the real axis, then this will be some exponential of C. This will be some exponential, some other value of C. Not exponential of C, but some P1, right? P1 plus C. P1 to P1 plus C. So if you map it, okay. I hope things are clear, but let me clarify it a bit more. Let's say you had P1 and P1 plus C here in the Mel scale. It will become exponential of P1 and exponential of P2. Or you can say exponential of P2 minus exponential of P1, where P2 is P1 plus C. This quantity, if my P1 is small, okay, you can take it like this, P1 common, exponential of C minus 1, right? This is constant, but this term depends on P1, right? If my P1 is small, this is the width of my window in the linear scale. So this width, right? This width is e to the power P1 times e to the power C minus 1, right? So here my P1 is large, so width is large. Here my P1 is small, so my width is also small. Clear, right? Now, if my width is large, I would like to decrease its amplitude so that the area under the curve remains same. So that's a small trick we use, that we normalize the W by this is basically, this quantity is this triangle filter whose amplitude is basically normalized so that the energy remains same. Energy remains same means if I take W energy of WB equal to 1, energy of this, and energy at WB equal to 5, let's say, they will be same. Energy means the area under the curve, let's say. Just take the area under the curve. It will be the same. All right. Um, okay, now let's come to the next part. We want to quantify the phoneme information. Uh, what we obtained so far is something like this: energy in these bands, right? But I don't want, uh, or I'm more interested in how this spectral envelope is changing shape. I'm interested in the shape of this spectral envelope. So one way to find that out is take a Fourier transform and take the low frequency coefficients, because low frequency coefficients of Fourier transform, they contain information about the overall shape, and ignore the uh, high frequency regions. Let me give an example. If I have a signal like this, uh, then my low frequency Fourier transform will take this uh, low frequencies will capture the shapes which are longer in time, right? My high frequency coefficients will capture the things which are smaller in time, right? That's why to get the spectral shape, I do another Fourier transform and take the low frequency coefficients. So we take another Fourier transform and take the lower coefficients. But FFT is complex, so we use DCT. Okay, is this point clear? I want to find the spectral envelope of my spectrum. First, I do the filter bank energies. And then on top of filter bank energies, I got 40 values, let's say. I will apply a DCT. And I will take the low frequency coefficients of the DCT. And that will tell me the spectral shape, the phonemic information. And this is what the DCT is like. I is the ith coefficient. So you know, in FFT, you multiply with exponential, complex exponential e to the power k something, right? But here you multiply with, uh, because FFT is complex, I want something real. Why do I want something real? Just to be more compact, just to be more, just make my things simpler. I want a real FFT. So ignore the complex part. What is the exponential of ij, I theta? Cos theta plus j sine theta. Ignore the j sine theta part. What remains the cos part? Just take that part and make another transform using that. It's called the discrete cosine transform. Same as FFT, but just that instead of e to the power I theta, I have cos theta. Right? So cos of I is like k here, k there, and b is like time here, n, b is like n here. So I is like the k of your, like the n of, and this is like again the n of, this is the k of your Fourier transform, right? Correspondence you can see. Same thing, right? There also you have 2 pi nk, um, 2 pi nk upon n, capital N. Here also you have pi I b upon capital B. Capital B is like capital N. This is like capital N. Okay. I goes from, now you can choose how many coefficients you want. Let's say your B goes from 1 to 40, but your I goes only from 1 to 13. You don't have to capture all those higher frequency coefficients also. Even 13 coefficients are sufficient. These are the common numbers used in processing, audio processing. Yes, yes, we are doing dimensional reduction, but we are doing it in a very intelligent way so that we don't lose any useful information, and we are able to compress as much information as possible in these 13 numbers, right? So it is dimensional reduction, but we are making use of all that auditory knowledge to compress it properly, to basically not miss any information. Like I know that in this, the information is only in the overall shape, right? And that can be best captured using simple DCT. So these CIs are called Mel frequency cepstral coefficients. Why Mel frequency? Because this filter bank was spaced, Mel frequency spaced, means it was linear in Mel frequency. So which means it becomes a bit distorted in the linear scale, right? And why? So mel frequency is clear. Why capstral? Capstral means you are taking FFT of FFT, right? This original thing was FFT, right? You got some energies from that FFT. On top of it, you are applying again an FFT or a DCT. So that's why it is called capstral. There is a theory of capstrum, etc., which we won't discuss. But the basic principle is this: we want spectral envelope, so take FFT of FFT or DCT of FFT transform. And then coefficients, because okay, these are just coefficients. So how many of you have heard about MFCCs before? It's a very common term. If you have worked in any audio project, you must have heard this mfcc features. But what is it actually? So this is what it is. They capture the phoneme information. Okay, a quick question now. Let me see how many of you are able to answer this. uh, how many of you know music, like ragas? How many of you know ragas? Raise your hand. Or you know the name or the concept raga, or something like raga is there. Okay. If I sing one rag versus another raga, and you want to distinguish the two ragas, you will convert your audio into some features, right? Let's say I converted using MFCC features. Can you distinguish between two ragas using MFCC features? Means if I give you spectrogram here, and for every spectrum in the spectrogram, I give you the corresponding MFCC coefficients, which means you get MFCC coefficient for every window in the spectrogram for one audio, and similarly for another audio. Now, can you distinguish the two ragas using MFCCs only? Yes or no? So basically, raga means different notes. I'm singing sa re ga pa dha sa. This is one raga. If I sing some other notes, it's some other raga. Let's say. Okay. You have better definition of raga for ordinary audience. Oh, let's make it. Yeah. Hmm. Okay. So let's simplify the question. I want to distinguish two different notes. I said sa versus I said re. Just two different notes. Can I distinguish them based on MFCCs? How many of you say yes? How many of you say no? The response rate is too low. The answer is, where is the frequency or pitch information? Where is the pitch information? Okay, tell me originally in the spectrum, where is the pitch information? It's in the, no, no, from looking at this spectrum, if I ask you what is the pitch of this audio, what will you do? Huh? The first peak or the comb spacing? Both are, uh, both may give you same answer, right? That's how you know pitch. Once you apply filter bank on top of it, what did you do? You destroyed that information. You blurred out all the peaks. You took a window and averaged it. Another window averaged. These are like kind of quite wide windows, right? So you destroyed that pitch information. On top of it, you took a DCT and the low frequency components, which means you took only the further smeared it down, further uh, blurred it out. So you cannot distinguish two notes based on MFCCs. You have deliberately destroyed that information. But the advantage is that if I say both these are, both these will have similar MFCCs because I'm saying But if I say E, and they will have different MFCCs. Is this point clear? So I've constructed a space in such a way that uh, my pitch information or the fundamental frequency information or the notes information that is lost, and my phoneme information is conserved. If I want to distinguish two pitches, ignoring the phoneme, what will you use? Spectrogram is, let's say, very high dimensional. You want to reduce it to some smaller space. To distinguish two different notes, what space would you like to use? Yeah, exactly. Simply F naught value. The scalar value is sufficient to tell you two notes are same or different. Okay. Okay, let's move on. I hope I have given you good food for thought. Keep thinking about it. Now let's come to, now using these observations, we can come to a theory called filter theory or source filter theory or source filter model. So what is filter theory basically? It's this: you have some input, you apply some LTI filter, linear time invariant filter, and you get some YN. We saw this in the last class also, right? And this LTI filter is characterized by something called HN. What is HN? HN is used to convolve XN. So my YN is simply XN convolved with HN. So YN is simply XN convolved with HN. So which you expanded, you get XK into H of N minus K, sum over all K. Right? Now, what is to get audio, let's say to get some sound, a sound. So the model is in this way. My input X is basically peaks at the F naught which I want. Right? My Xn is just the impulses or the peaks at the T naught which I want or F naught which I want, right? And then this LTI filter basically is like our mouth which shapes the sound. And here you get some at the same frequency. I think I didn't draw it very well. Maybe I will omit some. Okay, now it looks better, right? So my input was some impulse signals and output is the entire audio. So here is my pitch information. So where is my information? Here is my pitch and here is my phoneme. You can say pitch plus intensity because, and physically what is happening is when my lungs, when air comes from my lungs, it passes through some opening here, epiglottis, and those openings, they vibrate. If I want to sing a higher frequency, I will stretch it so that they vibrate at a higher frequency. If I want to sing at a lower frequency, I will keep it a little loose so that they vibrate at a lower frequency. So in this way, I can control the time period of these pitches, this signal. And when this signal, this kind of audio signal, it passes through my mouth cavity and nose cavity, it produces the sound I want to produce. For example, when I say, oh, what I'm changing? Same signal, same stretching of my epiglottis. What is changing is the shape of my mouth. If I say it's a sound. If I make my lips round, ooh, it's ooh sound. And by moving my tongue up and down, I say e. What's changing? Just tongue position, right? So by changing the shape of my mouth, I can generate different sounds. So, so this is how it looks like. Your pitch and intensity information is there in the input X. The phoneme information is there in the LTI filter, and the output is YN, which contains all three informations together. And if you look at this in the frequency domain, it is yk is xk into hk, because convolution becomes product in the Fourier domain. In the DFT domain, it is a product. So what is my xk? Xk is, let me use another color pen. So my xk is, let's say, this signal. What is my yk? Oh, sorry, hk. Hk is, let's say, the shape here, right? So what is my final output? Output will be like this. I've shifted it slightly so that you can see the two lines, right? And this is my final output signal. So this is called the source filter model. A source filter model, which means we are modeling audio with the help of LTI filters, linear time invariant filter. So here you can also see again, my input is like this COM structure. The height tells me the intensity, the spacing tells me the pitch. And then this, when it passes through this filter, it's like multiplication in the Fourier domain. You get the final spectrum out. Now this, all these things, X and H, are also changing with time. This is only for a small window. But if you see, the whole thing changes with time dynamically. So you get a quasi-stationary signal. That's why you use short time Fourier transforms to study these properties. Is that clear? Um, Now, when you look at these spectral envelopes, these envelopes also have their peaks, right? These are called formants. This term is new for you, I assume. Formants are basically the peaks in the spectral envelope. Just by knowing where are the formants, you can tell which phoneme it is. For a sound, formants are roughly in this location. For E sound, the first formant, second formant, third formant are roughly in this location. Generally, by using 3 formants, or some people use 5 to 7 formants, you can know which phoneme it is, right? So you all can become spectrogram readers. Just by looking at the spectrogram, you can tell what the person is saying. So there is a book called Quartieri. The author is Quartieri. Very good book, which discusses the mathematical, whatever mathematics I discussed in this lecture today. Many of these things are there in this book, speech signal processing book. No, it's independent of another frequency, because I say another frequency is different, but formats are same. Yes, the shape of the spectral envelope. See, they are decoupled, right? Here is the fundamental frequency, and here is the phoneme. They are decoupled. Okay, so
Sari ga re.
so now next time I'll just give you the spectrogram and I'll ask you what the person is singing. You can tell, right? One small catch is that some informations are, to get some informations, you need longer windows. Let's say the frequency information or the pitch information, you want longer windows. But for some other information, you may want shorter windows. For example, when she said ga, so the ga, the sound ga when the mouth opens, ga. And this is such a short sound. If you use a long window, you won't be able to capture it properly. So you need a shorter window to get the formants or whatever the spectrum representation right. All right. Okay. So can we read spectrograms? Yes, to some extent. There is a book called Acoustic Phonetics written by Professor Ken Stevens, who explained how you can, how spectrogram or how spectrum of every sound looks like. I mean, how to become spectrogram reader, not just visually, but also with programs. You can write a program where you give some spectrum, it will tell you which phoneme it is, right? Does it work in practice? This book came much before Alexa or Siri or these time. It was way back, even before machine learning, but it could not make Alexa or any commercial system because there are problems. There are real world challenges. When you speak fast, your formats are just lost. You won't get clear formats. Means at least you cannot programmatically or visually detect them clearly. Then if you have multiple overlapping sources, when somebody is coughing when I speak, my formats will be totally destroyed. But you can hear it clearly because you have learnt it. When there are people with speech disorders, when let's say I am a child who stammer, or I'm an old person with some neuronal disease, I don't speak very clearly, or I have some other speech problems like dyslexia, etc. Some small children, they have some problems by which, because of which they cannot speak properly. So how do you handle those sounds? That also is a challenge because the formats are totally different now. Musical structure, your audio can have a structure within itself. So how do you exploit that? So how do we make real applications using audio? So you design the representations. And our representation should be minimal in size, very compressed. We discussed some of these principles, right? Decibel scale, Bell scale, etc. They should be distinguishing for what we are interested in. If you want raga, don't go for mfcc, right? They should distinguish for what we are interested in, and they should be invariant to what we are not interested in. If you want phoneme, ignore the pitch information. Design the space so that it may have uniform sensitivity so that you get minimal size again. So that's why we use log scale, right? These are the principles which guided our previous lecture part. So for pitch, look for peaks. For instruments, look for spectral envelope. This we discussed. Okay. Now, when this started, when people started working in speech, it started with linguistic rules and signal processing. You have linguistic rules and you look at the spectra and try to predict what the person is saying by looking at formats, for example. But then people realized it doesn't work in practice. So people came to machine learning, and we got models like Gaussian mixture models combined with hidden Markov models. So that's how we made our first um, speech recognition systems, ASR systems, means speech to text conversion systems. They were based on GMM, HMM, the successful ones. If you have heard of Dragon, there was a tool called Dragon by Nuance company. So it was made using GMM, HMM, first commercial product, you can say. Then people moved to deep neural networks, and Alexa, Siri, Google, they all started with DNA and HMM approach. So Alexa came, the first model of Alexa was DNA and HMM based. And now we have moved to end-to-end machine learning where the input is the audio file, the raw audio waveform, no feature designing, no feature extraction, no engineering of that sort. Directly you map it to the words or phonemes. And what models do we use? We use end-to-end machine learning and sequence-to-sequence models, transformers, etc. We'll see more of this probably later. So when I say, hello, I'm giving this talk, it will give audio to text conversion. And we have so many commercial products because of this. And there are so many other domains where technologies are expanding: speech recognition, emotion recognition, clinical diagnosis, and of course, audio analysis, etc. Means what sounds are there in the room, etc. That was today's lecture, and I'll just summarize what we discussed. Some tools which I would like you to have a closer look at are Praat, Audacity, and Librosa library in Python. Very useful for what we discussed today. Some exercises, I have discussed them before. So thank you very much.